Welcome to Study Loop.
We're asked to calculate the separation between the ground state and the first excited state, and then we're going to compare that to the separation in the energy using the Bohr's model. So the energy expression for a particle in a one-dimensional box having length L is E sub n, where n is the energy level, is equal to n squared times Planck's constant squared divided by 8 times m, where m is the mass of the particle, divided by L squared, where L is the length of the box. So it is given that the volume of a cubical box, since it's a cube, the lengths are all the same, L cubed is equal to 4/3 pi a cubed if the volume is equal to that of a sphere. So here A is the Bohr's radius that was given in, the value was given in the question, 5.29 times 10 to the minus 11 meters. So if we substitute that in, we can get a value for L, since L is going to be equal to 4/3 times pi cubed, all raised to 1/3. So there's our expression for L. Plug those values in, we get a value for the length of the box at 0.53 times 10 to the minus 11 meters. No, just 10 to the minus 11 meters for length. Okay, so now we can use the formula for the energy of the different excited states to get the change in energy between the second and the first excited state. Delta is going to equal to E sub 2 1. So you usually replace n 2 and with 1 in these two expressions. So when n is equal to 2, in the above expression, we have 2 squared, which is 4, divided by 8. So that's 1/2. So this is going to be 1/2 h squared over ml squared minus, and then you plug in n equals 1. 1 squared is 1, so this is h squared divided by ml squared. So we just length box. Again, h is Planck's constant, so we're going to use units of electron volt seconds. So that's 4.136 times 10 to the minus 15 electron volt seconds, and the mass here is 0.511 times 10 to the 6 electron volt per speed of light squared, per c squared. So plugging these values in, and we find that this is equal to 155.5 electron volts. So that was one of the we were asked to find box. Next, for us, with the difference in energy level using the Bohr's model. Well, Bohr's model for the hydrogen atom is the energy levels are equal to negative 13.6 electron volts divided by the energy levels. So for Bohr's model, delta E prime is equal to, again, E sub 2 minus 1 energy states in the model are mentioned as negative 13.6 electron volts, which is the ground, divided by the energy level squared. So for E sub 2, this would be divided by 2 squared, which is 4. And then we're going to subtract from that negative 13.6 divided by 1 squared, which is just negative 13.6. Okay, so plugging those values in, we find that the difference in this energy level is approximately 10.2 electron volts. So we can box that in as part of our solution and let's compare them. So let's make a little comment of comparison. So we can say, upon comparing, we can see that the Bohr's model has a smaller energy setting. Make that larger, and that's the final part of our solution to the question.